Alright, now welcome back. This is the 2021 AB Calc FRQs. So, as always, there's going to be timestamps throughout the video, and within the description there's the link to the scoring sheet that AP releases. And just a heads up, these are slightly tricky compared to more recent ones, but they're actually not that bad once you read them and understand what they're asking you to do. So alright, let's get started with this first one, which gives us this chart, which models a bacterial population in a little petri dish, right? And so we're given the function and the distance from the center, or the radius, right? And so the first part is just asking us to approximate f prime of 2.25, right? So this is a derivative, and we don't really know if the algebraic function behind this, so we can't just take some derivative. Instead, what we're going to do is we're going to use the 2-point slope to get something that should be somewhat close to that, right? So we want 2.25, but we don't have that. So the closest we have is 2 and 2.5. So for this, it'll be approximately be f of 2.5 minus f of 2 over 2.5 minus 2. Alright, f of 2.5 is 10, minus f of 2 is 6, over 2.5 minus 2 is a half. So you get 10 minus 6, 4, over a half is the same thing as multiplying by 2, so you get 8 milligrams per centimeter. Now that's the first part of this question. Now you just have to explain what this means. And what this means is that at a radius of 2.25 centimeters from the center, the bacteria population is growing at a rate 8 milligrams per centimeter. And something along the lines of at a radius of 2.5 centimeters, 2.25 centimeters from the center, the bacteria population is growing at a rate of 8 milligrams a centimeter. Fairly straightforward, just 2 points slope. Make sure you include your units, because units will get you on this, but otherwise not too bad. Alright, now for part B, we're told that the total mass in milligrams of this population is given by 2 pi times the integral from r equals 0 to 4 of r times fr dr. Alright? But again, we don't have an expression for this, we just have a table. So we're asked to approximate the value of this integral using a Wright-Riemann sum with 4 subintervals. Alright? So we're going to have, 2 pi, that's just going to be a constant, times, first interval from 0 to 1, so we're going to use the function at 1, right? F of 1. 1 minus 0 is 1 times 1. But wait, this is r f of r, so you also have to include what the r value is, which is 1. Plus, from 1 to 2, we're going to use the function at 2. 2 minus 1 to get the change in x would be 1. And then the function, or the r value in this case is 2, so we multiply that by 2. Alright. Now we go from 2 to 2.5, so we're going to use the function at 2.5, right? The change in x in this case is just a half. And then the function itself is 2 halves. R is 2 halves. Alright? And now for this last one, it's going to be the function at 4 times the change from 4 to 2.5, which is 3 halves, times 4, and you should get this. Alright? But obviously, let's simplify this down a bit. Alright, so we're still going to have 2 pi times f of 1 is 2, times 1 times 1 is just going to be 2, plus f of 2 is 6, times 1 is 1, times 2 is 12, plus f of 2.5 is 10, times a half is 5, times 2.5 is 12.5 plus f of 4 is 18 times 3/2 times 4. Well, this is the same thing as multiplying by 6, so we're going to have 18 times 6. Now you may have noticed I did get lazy at the end, and once the numbers got too big, I did not do the actual math. Why does that matter? Because you can leave it as this form. Because this is, the first line here is sloppy. You can still simplify this down a fair bit. But this second one, yeah, you could continue simplifying. Like for example, you could get 2 pi times 14 plus 12.5 would be 26.5 plus 18 times 6. And you could also leave it as that. But these are all going to equal the same value, which is 269 pi. As you have a calculator, you could just find this value, but seeing as it will still accept this answer, and this will be less time, this one right here, I personally would just go with that and then leave it there. But yeah, that's the second part of this FRQ. Alright, now for part C, we're asked to find if our answer from part B overestimated or underestimated the actual mass. So first, let's just visualize this. We're going to have either a function that's increasing or decreasing, right? And we did a right Riemann sum. So if it's a decreasing function, let me curve it a bit more, so let's click, right? And these are subintervals. We're going to use this value, and this value. So this space that I'm shading in here is underneath the function, so it is part of the integral. However, we did not account for it, right? Because it was a right Riemann sum. If it was a left Riemann sum, it would be an over, right? Now we'll consider an increasing function of a right Riemann sum, right? We're going to have this, that, right? Now we're going to have all this space here. So there's going to be an overestimate if it's increasing, and an underestimate if it's decreasing. Okay, now how do we check if it's increasing or decreasing? For that, we got to take the derivative, right? So we integrated r f of r, right? So if we want the derivative with respect to r of this, that's just going to be a product rule. So we're going to have the left, derivative of the right, plus the right, derivative of the left. Derivative of r with respect to r is just 1, right? So the derivative of this is r f prime plus f. Okay, but how can we tell if it's increasing or decreasing? Well, we did it on the interval from 0 to 4, right? So r itself is positive. Okay, we know that's going to be some positive value there. Alright, what about f of r? Okay, well again, we have the table values there. It's increasing, it's all positive. So this is also going to be positive. And now our last value is f prime of r. Well, we can't get the exact values of f prime of r. We can tell, okay, and the slope from here to here is 1, here to here it's 4, and then it keeps increasing. Right? So we all then can also deduce that this is positive. So if this is positive, and this is positive on the interval from 0 to 4, we know the derivative is going to be positive. Right? So it's going to be increasing. Alright? So because the function is increasing, like this drawing, and we did a right Riemann sum, we're going to have some value over the actual. So we're going to be an overestimate. Right? But just saying that's an overestimate is not enough. You have to also justify why it's an overestimate. So it's an overestimate because the first derivative is increasing on that interval and we did a right Riemann sum. So since the derivative with respect to r of rfr is greater than 0 for r between 0 and 4, right? So we know it's an overestimate, but we also have to justify why it is. And something along the lines of, since the derivative of this is always positive on the interval from 0 to 4, we can deduce it's increasing, so it's going to be an overestimate. And that should get you the point for this part. Alright, now for part D, we're told that the density of the bacteria from R is between 1 and 4 is modeled by the function g, which is 2 minus 16 times cosine of 1.57 square root of r, quantity cubed. A mouthful, right? And we're asked for what value, k, does g of x equal the average value, or sorry, g of r, equal the average value of g of r on the interval of 1 to 4. Okay, what does that mean? We're at some point, we're going to call it g of k, where k is some number, is going to equal average of g of r, right? Okay, well, we can't find this just yet, but we can plug in, we know we'll have to plug in k for r here. But for now, let's just leave that alone. Now, how can we find the average value? Okay, well, we're given this expression. We can just use the average value formula, which is 1 over b minus a times the integral from a to b f of x dx. Okay, so we're integrating from 1 to 4, so we're going to have 1 over 4 minus 1, the integral from 1 to 4 of g of x, or g of r, sorry, dr, right? Now you're going to put this into your calculator, because that function is going to be a pain to integrate by hand. And when you plug it into a calculator, you should get a value of 9.875. So we're looking for where g of k is going to equal that value. Now how can we do that? Alright, well there's two ways. First, you can plug this into the calculator as one function, this as the other function, and find where they intersect. Or you can take this function and have g of k minus 9.875 equals 0, and then find the zeros. Either way, you will get the same value, which is k equals 2.497. Alright? And yeah, this is the most calculator heavy part of this FRQ, but it's not too bad. Alright, now for the second FRQ, we're told that there's two particles, P and Q, and we're given their velocities as a function of time, and we're also told that at t equals 0, particle P is at 5 and particle Q is at 10. Now just a quick note on notation here. X of P refers to the position of particle P. V of Q refers to the velocity of particle Q. Alright? The subscript is just which particle it is. But for this first part, we're asked to find the position of both particles at t equals 1. Alright? So to get position, when you're given velocity, you have to integrate. Right? So the integral from 0 to 1, why 0? We know the value of P's distance at 0, and we want it at 1. So we're going to need something that we know to get something that we want. Vp of t dt, that's just going to be the position of P at 1 minus the position of P at 0. Right? So to get the position of P at 1, it's going to be the integral from 0 to 1 of the velocity of P plus its position at 0. Alright? So now you're going to plug this into the calculator because you don't want to integrate this by hand. It will not be a fun time, but integrate that and then add 5, and you should get a value of 5.371. Alright? Now, let's move on to the other particle. Same thing. We're going to have the integral from 0 to 1, Vq of t dt is the position of q at time equals 1 minus the position of q at t equals 0, right? Same thing, x sub q of 1, not 0, whoopsies, is just the integral 0 to 1 vq of t dt plus x cube of 0. Alright, once again, plug this into the calculator, save your time, don't try and do it by hand, but you should get a value of 8.564. And that is the first part of this FRQ. Now for part B, we're asked if the two particles are moving toward each other or away from each other. And for this, you just need to know two things about each particle: where they're at and which way they're going. So we already know where they're at from part A, right? We know that, let's call this blob right here particle P, right? 5 point something something. And then particle Q is further away, right? So this is going to be 0, right? So it's going to look something like this. But now we just got to figure out where they're going, right? So for that, we need the velocity. So Vp of 1, because this is asked for time equals 1, is going to be sine of 1 to 1.5. It's just going to be sine of 1, which is positive. You do not need the actual number, or the actual value, you just need to know the sign. Right? And then you got to do the same thing for VQ. Right? So we're going to have 1 minus 1.8. So we're going to have negative 0.8. And then times 1.25. Okay, so what does that mean? That means P is going this way, and Q is going this way. As a positive value means we're going to the right, and a negative value means we're going to the left. So, with this, we can now conclude that P and Q are moving toward each other at t equals 1, but you have to explain your answer. So, how can you explain your answer? Well, I think as long as you show that you calculated V of P and V of Q respectively, and you have a diagram here with their position and their velocities represented as an arrow, and then some sentence saying, since Vp of 1 is positive and Vq of 1 is negative, they're going towards each other. Something along those lines will convey all the information you know to your grader, and with that they should be able to just give you the point and move on. Alright, now for part C, we're just asked to find if the acceleration of particle Q is causing it to increase its speed or decrease its speed. But that's acceleration, shouldn't that be velocity? No, because if your velocity is going this way and your acceleration is going that way, it's pretty much like hitting the brakes on a car. You're going to slow down. If they're going in the same direction, then you're accelerating. Alright? So first, we need to find out the velocity of Q at t equals 1. Alright, so Vq of 1 is just 1 minus 1.8 times 1.25 to the first, which is just 1.25. Right? 1 minus 1.8 is negative 0.8, but that can be written as negative 4 over 5. This can be written as 5 over 4. And you see, those are going to cancel out nicely, and this is going to equal negative 1. Alright? Now, for part D, the next part of this, for part C, not part D, right? We need the acceleration of Q at t equals 1, which is the same thing as the derivative of the velocity at t equals 1. Alright? So just plug this function into your calculator and find the derivative at t equals 1, and you should get approximately 1.028. So what does this mean? It means our velocity is trying to go this way, but our acceleration is going this way. So we're actually going to be slowing down. Now, how can you write that? If you write something along the lines of, since the velocity of Q is negative and the acceleration of Q is positive, Q is slowing down, that should give you the points for this FRQ. Alright, Now, for part D of this FRQ, we're asked to find the total distance traveled by particle P from t equals 0 to t equals pi, right? So you're probably thinking, okay, to go from velocity to position, I just got to integrate. And you're correct, but there's one small key difference. We want the total distance, so we're going to integrate the absolute value of velocity. So the integral from 0 to pi, absolute value, velocity of particle P, that is going to give us what we want, which will be 1.931. And then you just have to write a sentence saying P travels 1.931 between t equals 0 and pi. Oh, we'll write that as an inequality. And just like that, that's this FRQ done. Alright, now for FRQ 3, we're told that some company designs spinning toys with using this family of functions where c is just some constant. Alright, for part A, we're asked to find the area in the region of the first quadrant between the x-axis and the graph of this when c equals 6. Right? So we know we're going to have some integral, c is going to equal 6, x square root 4 minus x squared dx. Alright. But now how can we find the bounds? Well, we know it's going to be in the first quadrant and above the x-axis. And the graph they gave us looks something like this. So one of these two has to become 0. Right? So if we have x equals 0, we're going to have 0 times square root of 4. That's still going to be 0. That's the first bound. Now, to set the inside of this equal to 0, we need 4 minus x squared to equal 0. And that happens when x is plus or minus 2. But because we're only in the first quadrant, we only want positive 2. So that's the integral that we're going to do. Alright? Now I'm going to take out a 3 from this integral because we can 3 times 2x is the same thing as 6x, that's why that works. Square root of 4 minus x squared dx. Now you might be asking, wait, why did you take out a 3? It's going to be the same result. You're right, but as you can tell, or hopefully can tell, this integral is going to be u sub. U is going to equal 4 minus x squared. Du is going to equal negative 2x dx. So negative du equals 2x dx. And what that means is now this becomes du, which is going to be necessary for this integral. So 3 times the integral of x equals 0 to x equals 2. Please keep track of your bounds. Square root u du. Alright. This is the same thing as u to the half. A half plus 1 is 3 halves. Alright. Then you divide by that new power. Plus c. Although we won't be needing that because this is a definite integral. Right? And we're going to evaluate from x equals 0 to 2. Alright? But to do that, we first got to bring it back to the x world. Alright? So, quick simplification. 3 times 2/3 is just 2. U was 4 minus x squared. Alright? So now we just got to plug stuff in. Well, if we plug in x equals 2, we're going to get 4 minus 4. That's 0. Alright, that's wonderful. That's a very nice easy plug-in. Now if we plug in x equals 0, we're going to get 2 times 4 to the 3 halves. Alright? 4 to the 3 halves is the same thing as 2 squared to the 3 halves. Exponent properties, this becomes 2 cubed. Right? So then you get 2 times 2 cubed. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So you get negative 16. But wait, this is an area, it can't be negative, so it has to be positive 16 inches squared. Where did I get the inches squared from? At the very end of the introduction paragraph for the question, it says x and y are both measured in inches. So that is part A. A bit of a weird FRQ, but it's not too bad. Now for part B, we're told that the derivative of those functions is modeled by this, and that for some particular toy, the largest, that's a very key word, cross-sectional area is 1.2 inches. What's the cross-sectional area? Like, what variable is that? That is y. So we know y equals 1.2, and we have to find x. And here's how this works. Because we want the largest, that's going to be a maximum, so the derivative is going to equal 0. Okay? So we're going to have 0 equals this mumbo jumbo. But we don't need to solve all this mumbo jumbo. We just have to make the top equal to 0. So we're going to have c times 4 minus 2x squared equals 0. Alright? Well, we just need to make the inside equal to 0. Alright? So that's going to be divided by 2. We're going to get 2 minus x squared equals 0. X equals positive root 2. Why positive? We're still only going to be working in the first quadrant, so it doesn't matter for the negative square root of 2. Okay? So now, we know that x is going to equal square root of 2. And so we have to put this back into the original. Right? So you're going to have 1.2 equals c times the square root of 2 times square root of 4 minus the square root of 2 quantity squared. So we'll get this expression. Alright, the square roots here are going to cancel out. So we get 1.2 equals c times the square root of 2 times square root of 4 minus 2. Right? Not too bad. 1.2 equals c square root of 2 times square root of 2, because 4 minus 2 is 2. We have two square roots, those are going to cancel and just become 2. 1.2 equals 2c, c equals 3/5 or 0.6, whichever you prefer. And it looked like a mouthful at first, and there's a lot of things you're just like, whoa, where is this all coming from? That's understandable. You should not be discouraged. You should just then take a step back, think slowly, and figure out what they're asking you to do and how you can do it. Okay? But yeah, your final answer should be c equals 0.6 or 3/5, whichever you prefer. I'm probably going to leave that at tape. Me dropping a marker. Part C of FRQ 3, we're told that some other toy has a volume of 2 pi cubic inches, and we're just asked to find what's the C value for this toy. Well, we know that 2 pi is going to equal the volume, right? But how can we get volume? Well, it's going to be the integral of something squared times pi. Okay? We're going to have 2 pi, that's a poorly drawn pi, there we go, equals pi, the integral, in this case, this, cx square root of 4 minus x squared, quantity, the whole thing squared, dx. Alright, but how do we get the bounds of integration? Because we need those. If not, it's just going to be indefinite, we're going to have a plus c, it's going to be messy. Well, no matter what the c value is, so long as x equals 0 and x equals 2, this whole thing is going to equal 0. So it goes from 0 to 2. Alright? Now let's divide both sides by pi. Alright? And now let's multiply this out. We're going to get c squared x squared times 4 minus x squared. Now remember, c is not a variable, it's some constant, so we can pull it out of the integral. So 2 equals c squared, integral from 0 to x squared times 4 is 4x squared, x squared times negative x squared is negative x to the 4th, dx. Alright, not too bad. This is just some polynomial, so it's just a power rule now. You get 2 equals c squared times add 1 to the first power, you get 3, then divide by 3, so 4/3 x cubed, minus, add 1 to the power to get 5, so you get x to the 5th, divided by 5, so a fifth of that, evaluated from 0 to 2. Okay, well, if we plug in x equals 0, we're going to get 0, that's good, so we know that's going to be something here, minus 0, which is really just that something. Alright, now comes the tricky part though, because then you have to plug in 2. So we're going to have 4/3 times 2 cubed minus 2 to the 5th over 5, and then all of that times c squared. Whew! Now, this is some annoying math with fractions, but it's actually not going to be that bad. Alright? So again, 2 equals c squared times 2 to the 3rd is 8. 8 times 4 is 32. So 32 over 3 minus, alright, 2 to the 5th, that's 2 times 2, 4 times 2, 8 times 2, 16 times 2, 32. So 32 over 5. Okay, now what can we do? Well, now, because this is a FRQ and you are a human being, you're not going to try and simplify this. Instead, what you're going to do is divide both sides by this. 2 over 32 over 3 minus 32 over 5 equals c squared. And now you're just going to take the square root of both sides to get c equals the square root of 2 over 32 over 3 minus 32 over 5. And you are correct in assuming that this is just very messy. There's got to be some way to simplify this. You're correct. It's the square root of 15 over 32. But this is an FRQ. You do not have to give it in the simplest form. This is equivalent to this, and you still did your math right. So you can just write this down and move on and be happy that you don't have to simplify this. Alright, now for FRQ4, we're given this graph of f, and we're told that g, or some other function, is defined as the integral from 0 to x f of t dt. Alright? Now this FRQ is fairly straightforward, so let's get straight to it. The first part is asking on what intervals is g concave up? Okay, whereas for concavity, we need the second derivative. So g prime of x is f of x, and g double prime of x is f prime of x. Okay, that's good to know. And we're asked for concave up, which means it has to be a positive second derivative. So what that is saying is that we're looking for where f prime of x is positive, aka where the slope is positive. So we're going to have positive slope from -4 to -2 and 2 to 6. So for part A, it's just from -4, 2 with 2, 6, since f prime of x is positive. And that is all you need to write down for this first FRQ, because it is fairly straightforward. Alright, now for part B, we're told that p is a function such that p is g of x times f of x, right? And we are asked to find the derivative of p at x equals 3, which is going to be left derivative of the right, so f of 3 times g prime of 3, plus right derivative of the left, g of 3 times f prime of 3. But wait, in part A, we deduce that g prime is equal to f of x, and f of 3 is -3. So we'll have p prime of 3 equals -3 squared, plus, here we're going to have f prime of 3, which is just 1. And now I did save g prime of 3 for last because it's the most annoying to calculate, because it's the integral, sorry, just g, not g prime, from 0 to 3 f of t dt. Alright? So what does that mean? It Now, that just means we're going to have to find the area under the curve, which is shaded in red here. Now, my drawing is not to scale nor perfect, however, the one on the PDF or the pages that they gave you is. So I'll probably post it up somewhere here and show you more clearly, but essentially, this triangle has the same area as some triangle here. So those two areas, one is positive above the x-axis, other one's negative below the x-axis, they're going to cancel out. So then what we are left to find is this little tidbit here, right? Which is really just a rectangle with length 3, base 1, and a triangle with base and height of 1. So it's going to be 3 plus 1/2 times 1 times 1, which is going to be negative 3/2, because again, we are underneath the x-axis, okay? So then we're going to have times negative 3.5. So p prime of 3 equals 9 minus 3.5, which is the same thing as 18 over 2 minus 7 over 2, which is 11/2, or 5.5. And that'll be part B. Alright, now for part C, it's fairly straightforward. We're just asked to evaluate this limit, which is the limit as x goes to 2 of g of x over x squared minus 2x. Alright, well, the first thing I notice is that we're going to have 2 squared minus 2 times 2 on the bottom, which is going to be over 0. So we need to show that this is most likely going to be a L'Hopital's rule. Alright? So what that means, we want g of 2. Okay, what is that? That's the integral from 0 to 2 f of t dt. Alright? What that means is the area of this triangle minus the area of this triangle. And they are, like I mentioned in part B, they're the same triangle, except one's positive area, one's negative area. So this is going to equal 0. Alright, so now we've shown this is an indeterminate form. Now we can do L'Hopital's rule. When we do that, we'll get the same limit, but now it'll be g prime of x over 2x minus 2, which is the same thing as f of x over 2x minus 2. Alright? If we plug in 2 on the bottom, we're going to get 4 minus 2, which is going to equal 2. On the top, f of 2 is negative 4. So you get negative 4 over 2. So this limit, when you evaluate it, comes out to negative 2. Alright, now for part D, we're asked to find the average rate of change of g from negative 4 to 2, and then asked if by the mean value theorem there exists some c such that g prime of c is the average slope. Alright, let's start finding the average slope, which is just going to be g of 2 minus g of negative 4 over 2 minus negative 4. 2 minus negative 4 is 6. We applied this in part B, found this in part C, but g of 2 is 0. And now g of negative 4 is this area here, which you can break up into these 3 shapes here, being 2 triangles and a rectangle. I'm going to flash up the PDF and show you guys the edited version so it actually looks nicer and you can see it much better. But when you evaluate that, you're going to get negative 16. Right? So you're going to have 8/3 as your average slope. So now we're asked if there is some average value if there's some value on the interval from negative 4 to 2, so that g prime of c equals this. Alright? This is the mean value theorem, so what we're going to do is we're going to get g prime at the endpoints and see how it behaves. So g prime of negative 4 is going to be f of negative 4, which is 0. Right? And then g prime of 2 is f of 2, which is going to be negative 4. Alright, so now that we have our average slope, and we know that g is differentiable and continuous on this interval, we know that, yes, since by the mean value theorem, there exists some c such that g prime of c equals 8 over 3. And that's it for this FRQ. Alright, for this FRQ, we're just given a function of an implicit function, which is 2y squared minus 6 equals y sine x. Part A is fairly straightforward. We're just asked to show that the derivative is what they give you. So we're going to differentiate this to get 4y dy dx. Get rid of 6 is 0 equals y sine x. That's going to be a product rule. So y cosine x, left derivative right, plus right derivative left, which is going to be sine x dy dx. Alright. Move the sine x to the other side and factor out the dy dx. And now you just simply divide both sides by 4y minus sine x to get what they gave you. dy dx equals y cosine x over 4y minus sine x. And that is fairly straightforward. Alright, and now for part B, we're asked to write the line tangent to the point at 0, 3. So okay, we're going to need two things. Point values, which we have, and then the slope. Alright, to get the slope, we're just going to plug in 0, square root of 3 into the derivative. So we're going to have square root of 3 cosine of 0 over 4 square root of 3 minus sine of 0. Okay, square root of 3 times cosine of 0. Cosine of 0 is over here on the unit circle. That's just going to equal square root of 3 because it's 1. Right? And now sine, same place, except it's 0. So it's going to go square root of 3 over 4 square root of 3, which is a fourth. Alright, now we need the equation line. So it's going to be y minus square root of 3 equals 1/4 of x minus 0. And that is it for part B. Fairly straightforward. Alright, now for part C, we're asked to find on the interval from 0 to, where x is from 0 to pi and y is positive, where the tangent is horizontal. Right? So we're going to set dy dx equal to 0. So we get y cosine x over 4y minus sine x equals 0. And now we're going to set the top equal to 0. And we're told that y has to be positive, so y cannot be 0. So we're looking for where cosine of x is equal to 0 between 0 and pi. Well, that's going to happen somewhere up here. That's going to be pi over 2. So x is pi over 2. Alright? Now, we have to check two things. First, that this point exists on the graph. And second, that y is positive at this value. Okay, so now let's just check for in the original function, we're going to check if this value even exists. Right? So we're going to get 2y squared minus 6 equals y sine of pi over 2. Sine of pi over 2 is up here again, and that's going to be equal to 1. So you get 2y squared minus 6 equals y. Rewrite this, 2y squared minus y minus 6 equals 0. Alright, now we have to factor this. Well, our leading coefficient is a 2. So we're going to have 2y something, y something. Okay, alright. So now that we've factored this somewhat, we know that's going to be a 2 here, and there's going to be different signs. Alright, how do we get the actual values now? Well, we know it has to multiply 6, so it's going to be 1 and 6, or 2 and 3. And we know that they're going to have different signs. Okay, so, let's see. But they also have to add up to -1, which is why 1 and 6 are not it, it's 2 and 3. But now we have to figure out which one goes where. Alright, well this is tricky at first, admittedly, because it's either this, which is a very poor 3, or you can flip them around and get this. Okay, how can we tell which one's which? Well, you just have to multiply it out and see. You're going to get 2y times y, y squared, 2y times negative 2, negative 4y, 3 times y plus 3y, 3 times negative 2 is negative 6, 2y squared minus y minus 6, that's what we want. Let me prove that the other one's wrong by multiplying it out. Alright, well we know the n terms are going to be the same, right? 2 times y is 4y, or sorry, 2 times negative 2y times negative 3 is negative 6y. And then you get 2 times y, you're going to get 2y. 2y squared minus 4y minus 6, that's not what we want. Alright? So now we have this, we know y is going to equal negative 3 halves or 2, but because y has to be positive, y will equal 2. So at pi over 2 comma 2, y has a vertical tangent, or horizontal tangent, not vertical. Alright, now for part D of this FRQ, we're asked to determine if f has a relative minimum, maximum, or neither at the point we just found. So you cannot do a first derivative test on this because it's an implicit function. So instead we're going to check the concavity at the same point. So yes, we have to take the derivative of the derivative, which is going to be low d high, so 4y minus sine x, times the derivative of this, and it's a product rule, so it is going to be a mouthful, but left derivative of the right plus right derivative of the left. Now that's low d high minus high d low minus y cosine x times d low is going to be 4 dy dx minus cosine x all over low squared. Okay, so now comes the very annoying part of plugging stuff in. Right, so again, this is at pi over 2 comma 2. Okay? So let's just knock out the bottom first. Let's see what we get. We're going to get 8 minus 1 quantity squared. Okay? Now the top is going to be annoying because we're going to have 4y minus sine x. We plug those values in, we're going to get the same thing, which is going to be 7 times negative y sine x, so negative 2 sine of that, so that's going to be negative 2, plus the derivative, which we have to now plug it into the original up here. Alright? But here's the good thing. It should come out to be 0, because this is where we found that it had a horizontal tangent. So plus 0 minus y cosine of x, that's from the derivative. We know if we plug that in, it's going to be 0. 0 times something here, right? So this is going to simplify to negative 7 times 2 over 7 squared. Again, once I notice, hey, the derivative is 0, I don't have to plug everything in. Wherever I see y cosine x, I know it's going to be 0. That includes the derivative. That's how we cut down on these calculations. We simplify this to get negative 2 over 7. Okay, now we just did all that math. What does this tell us? So, because the second derivative is negative, it's concave down, right? And if a function is concave down, that means it can have a maximum. So, what you're going to write is, since f double prime of x is less than 0, the answer from part C is a maximum. And that will conclude this FRQ. At the end, it did get a little bit tricky, but just try and think of how you can reduce the calculations you have to do. Alright, Now for the first part of FRQ 6, it's a slope field. Once again, movie magic or something, you're going to see it up here. Just draw a straight line for 0, 0. Well, not a straight line, but the line that passes through all appropriate slopes. Alright, now for part B, we're asked to determine, or interpret, the limit as t goes to infinity of a of t equals 12. We're pretty much asked, what does that mean? Alright? What that means is that over time, the patient only receives 12 milligrams of medication because that's what this FRQ is about. So as long as you write something along the lines of, over time the patient receives 12 milligrams of medication, that'll get you the point for part B, which pretty good start to this FRQ so far. Now for part C, we're asked to do separation of variables on this equation and find a value, or an equation, with the initial condition of a of 0 equals 0. Alright, well, let's divide by 12 minus y and multiply by dt to get dy over 12 minus y equals a third of dt. Now we're going to integrate these. Alright, this is just going to be fairly simple, 1/3 of t plus c. This is going to be u sub with u equals 12 minus y, du equals negative dy. So this becomes the negative integral of du over u. That's going to be a natural log. So we get the negative natural log absolute value of 12 minus y equals a third of t plus c. Alright? Now, here's what I'm going to solve for c. Because we know at x equals 0, y equals 0. So you get the negative natural log of 12 equals c. Alright, now let's bring it back up here. I'm going to rewrite the equation and then we're going to solve it in terms of y. Alright, now the first thing I'm going to do is multiply by a negative on both sides. So just get the ln, not the negative ln. Now the opposite of the natural log function is e. So we're going to raise this all to base e. So we get 12 minus y equals e to the negative 1/3 of t plus ln of 12. But wait a minute, ln of 12 and e are opposites, and we can rewrite this as e to the negative 1/3 of t times e to the natural log of 12, and then these will cancel out, and it'll just leave us times 12. Alright? Now we're going to subtract 12 from both sides. And multiply by negative 1. And that right there is our solution, or answer to part C. Alright, now for part D, we're told that some other medicine is modeled by this differential equation, and that at t equals an hour, there's 2.5 milligrams of the medication in this patient. We're asked to determine if the rate of medication is increasing or decreasing at t equals 1. And again, we're going to have to do the second derivative. Derivative of 3 is 0. Now this is a quotient rule, so we're going to have low d high minus high d low over low squared. Alright? And now we just have to plug in these values. Alright, so we're going to have dy dt at this is 3 plus 2 halves over 1 minus 2. 1 minus 2 is going to be negative 1. So 3 minus 2 halves, so it's going to be positive a half times 1 minus 2, negative 1 minus 2.5 over negative 1 squared. And this is going to be negative 1 minus, negative a half minus 2.5, negative 3. Right? So it's going to be some negative value. Alright, so because it's a negative value, what that means is that it's going to look something like that. So it'll be decreasing. So, since I believe they refer to this function as b, so b double prime of t is less than 0 at t equals 1, b is decreasing at t equals 1. And so, yeah, that's the last FRQ. This part can be a bit tricky because it's another differential equation and asking about minimums and maximums. So overall, not the hardest FRQs on the planet, but if you slow down and think a bit, you should be fine. And so yeah, thank you for watching. If you found this helpful, consider leaving a like. And if I really was helpful, maybe subscribe. If I can improve somewhere, please let me know in the comments. I always try to read them. And yeah, have a good day.